Well, we determined that in one of my grad classes the other night that my wife, I'd like to go visit India at some point. My wife doesn't want to go because of the squat toilets. Okay. There's some concerns regarding the lack of westernized plumbing. Well, then I find out that most of the hotels and stuff all have westernized toilets and stuff. But the real problem is that apparently India just has like thousands and thousands of wild dogs just wandering the roads and stuff. Like it's a problem over there. My wife has a phobia of dogs. So now that's the bigger concern. Is we all remember the situation with the trip to Egypt this last. We went in June. My wife and I went with our church group to Israel, and then I wanted to do the extension trip into Egypt, and she was convinced she has a sensitive stomach and she was going to end up in an Egyptian hospital. All right. So she showed me a picture of what she thought the average Egyptian hospital room looked like. What do you think she showed me? Okay. She showed me a room, that kind of rundown room with 3 live cobras in it. Okay. That's what an average Egyptian hospital looks like. That or apparently stray cats or something. I guess Egypt has an issue with cats. I said, well, you want the cats or you want the cobras?
I remember it last semester. I looked it up when you told us, and that's what comes up for Egyptian hospitals.
The picture of cobras?
No, it's just a bunch of cats. And
oh, yeah, cats
really
everywhere.
Dirty hospital.
Well, she likes cats.
Yeah.
Yes, I mean, that's like a perk, right? But what's funny is when we were in Israel, she was taking all the preventative stomach meds and stuff. Out of the whole group, she was the only one that didn't have any issues. There's only so much hummus that the American digestive system is capable of handling in a short period of time. All right, so homework, we were starting linked lists, add front, add end, and display. All right, how'd that go? Besides, Alex is a good tester code. It's like, look, it may have gone fine. I just don't know. All right, let's see where we at. I got too much crap in here, don't I? All right, yeah, we'll build it in here. All right, so we're going to create a linked list class. And we're going to create a node. So we'll create a new class. Call this guy linked list. We'll create another new class. Call this guy node. All right, and we decided a node is going to have a payload and a next node. We doing ints, strings? What are we doing? Strings? All right, so we'll have a private string payload. So that's the value that a particular node holds. And then we'll have a private node next node. So this guy knows about the next node in there. Then we need our constructor for our nodes. When we build a node, we'll go ahead and pass it the payload with which we're building it. And then we'll default next node to null because it doesn't currently point anywhere. All right. So we have public node string payload. This dot payload is equal to payload. And then we'll say this dot next node is equal to null. It probably defaults to null, but if you want it to be null, set it to null. All right. Now we're definitely going to need the ability to get the payload. And we won't necessarily need the ability to set the payload, but we will need the ability to get the next node and set the next node. But rather than write it right now, just to kind of take you through the process, I'm going to leave it like this right now because this is what I know for a fact we know we're going to need right now. As we get to the point where we need to set the next node for a node, we'll come and add that ability. So we kind of let it organically grow. Okay, so we'll pause node here for a moment. Okay, so our linked list is a collection of these dudes, right? Where one node has a value, it then points to another node through its next node thing. It has a value, which then points to another node, which has its value, so on and so forth. Now our linked list All that guy is a single node that points to the front of the list, where everything starts. Okay? So linked list, this guy will have a private node called head. Then we'll have our public constructor for this guy, public linked list, takes no parameters. We'll say this dot head is equal to null. Now, just thinking forward a little bit, at some point we might want to kind of add a count or something like that to kind of keep track of when the list gets bigger or smaller. But for right now, we don't know we need that. Okay, just kind of thinking about features we might want to have about a linked list, because one of the we could say weaknesses with a linked list. You know, remember we talked about linked lists versus arrays, and kind of the trade-off is arrays are fast but memory inefficient. Linked lists are slow but memory efficient, because we don't have to have all those nodes right next to each other in memory. This node lives over here in memory, which then points to the next node, which lives over here in memory, which then points to the next node, which lives over here in memory. So we don't have to have all this memory contiguously available. So we can arbitrarily just grow and shrink the linked list without doing any destruction, right? If we get rid of something, we're destroying one node, all right? So with that in mind, to count the number of elements in a linked list, if we weren't keeping track of it all along, we have to literally start at the beginning of the list and traverse the whole thing, counting each time we find a node until we finally hit a next node that's null. Every single time we want to get the count, we have to traverse the entire list. So we can kind of think ahead and say maybe that's not the best idea. We're going to still write it today as you know, instruction and type stuff, and then we'll say, hey, you know what? If every single time we added a node, we incremented count, and every single time we subtracted a node, we decremented count, we don't have to traverse the whole list for the count anymore. That'll be our upgrade. Okay, just thinking ahead. But by default, linked list is just this dot head is equal to null by default. Now, we were supposed to write for today a add front, add end. All right? All right. So we'll say public void add front. And what we'll do is we'll go ahead and we'll have add front take in a string, and then we'll build our node and then have that guy get added to the front, as opposed to making the end user call add front with a node. Now, it might actually benefit us eventually to have two versions of add front. One version that takes a node as a parameter, and another version that takes a string as a parameter. Okay, what's it called when we have two methods with the same name but a different number or type of parameter? Polymorphism. All right, so this guy will take in a string s as a parameter. We'll go ahead and build a node n is equal to a new node, passing it s. So we build a node there to connect this guy. Now we are adding this dude to the front of our linked list, right? So regardless of what the list currently looks like, when all is said and done here, head is going to point to this new guy. But we need to make sure that we don't lose the node that head currently points to. So we can ask the question, if head is equal to null, if I'm currently dealing with the empty list, then this is as easy as saying this dot head is equal to n. All right. So if this is the first guy I'm adding to my linked list, that is the case where head is currently equal to null, the front of the list is currently equal to null, then I'm just going to go ahead and make the front of the list point to the guy I just created, which will make his pointer count go from 1 to 2. Correct? So right here, this node that got created right here has a pointer count of 1 because n points to him. Now he has a pointer count of 2 because this dot head also points to him. When add front ends, this variable goes away. It's out of scope. So the pointer count will go down to 1, but since it's still greater than 0, automatic garbage collection is not going to come and clean up our node. Right? That's why it's important we make head we ultimately make sure things are pointing at everything. All right, so if we have the empty list, this is our easy case. Set head equal to that guy. Otherwise, what we need to do is we need to insert the new value n to be the new front of the list. So we need to have n point to the same place that head currently points to. Then we set head equal to the new guy. All right, so if we're in here, this means that head points to a real node. So we'll say n dot, I need to be able to set n's next node. Okay, so I have a weakness here in my node because I'm not able to set his next node because it's a private variable. So we'll go ahead into node here. We'll add our set next node. Okay. I'm also going to need to be able to get the next node because I'm going to have to say head. I want to set. N's going to say I want to set my next node to your next node. So I need to get your next node so I can set my next node equal to that guy. So we're going to need a getter and setter for next node. So source, generate getters and setters. And I'll just click on next node for right now. All right. So there's our getter and setter for next node. And then we'll fix Eclipse's bad programming, also known as Emma style programming. Right? You do this stuff, right? Yeah. Garbage.
I let it generate for me, and I let it sit.
You leave it? Oh my gosh! How can you stand it?
Test myself.
Huh?
I tested myself to see if I could go and not change it, and I didn't change it.
Was it difficult?
Yeah.
Really?
Yeah.
I see. I've trained him well. All of my students, like 10 years from now, there's like horrible psychosis. It's like a OCD. They like can't leave a room without like folding napkins a certain way and stuff.
Well, I'm just afraid I'm going to get somewhere, and when I'm writing code, they're going to tell me not to indent it.
Oh, they'll tell you to follow the other standard. I mean, it really doesn't matter. At the end of the day, I don't know. I just think that looks so bad.
Yeah. Feel bad.
I'll just quit for the
What's this?
I'll just find another job until they let me drive me nuts.
I don't know if it's worth that. I don't know if it's that bad. Just at the end of the day, it's like a personal preference. Like for instance, let's say you worked for Coca-Cola, but you're really kind of a Pepsi fan, right? You probably don't sit in the Coca-Cola cafeteria drinking Pepsi. You just got to drink Coke, right?
I'm bringing my Pepsi in the Coke bottle.
You go that far? Oh, so you're one of those guys. So you go to a restaurant and you say, "Oh, I'll have a Coke," and say, "Oh, we have Pepsi products." They'll say, "Okay, I'll just have water." You're that guy?
No.
You won't drink. You'll drink both.
Yeah, I'll drink both. Yeah.
I don't understand those people.
I think Coke tastes better.
Well, fair enough. I mean, my favorite cola, I drink diet, so I like Coke Zero. I think it's the one that tastes the most like a regular soda. I think Coke Zero tastes a lot like regular Pepsi. Remember, was it Crystal Pepsi or Crystal Coke? I think it was Crystal Pepsi years ago. This is in the 90s. They had clear cola. So I think it was Crystal Pepsi. Crystal Diet Pepsi tasted exactly like classic Coke. I mean, indistinguishable if you closed your eyes. All right, so we got our getters and setters. So now I can come over here, and I can say n dot set next node to this dot head dot get next node. Okay, so now n points to the same place that head points to. That make sense? After I've done that, then I'll say, here, we'll help Alexis out there. Okay, so after I've set the next node for n to point to the same place that head points to, and actually, it's not head get next node. It's just head. Because otherwise, we would be skipping the thing that head currently points to. All right, so I'm going to set n to point to the same place that head also points to. Okay, so both of those guys point to the same place. Then I'm going to say this dot head is equal to n. Make sense? All right, so now actually with that in mind, we didn't even need this first if statement. Because we could just say this dot head equals to n. Oh, actually, no, we do need it because we ultimately did the update n in this other case. So that's add front. So before we do add in, let's go ahead and write our display method. All right, so we can test add front, make sure we can add stuff to the front of our list, and we can continue to display it. So our display method is going to effectively traverse our list from node to node to node until we finally hit a node that doesn't have a next node, whose get next node returns null. All right, so we'll have public void display. All right, and we'll ask the question of this dot head is equal to null. Killing me. Then we'll just maybe do a print out empty list. Something along those lines. Else, we're in here, that means we actually have stuff, right? We got stuff to traverse, at least one node. All right, so because we don't want to break our list, we can't move the value of head. Right? That guy always needs to point to the beginning of the list. So I'm going to need another pointer that I can use to traverse my list. All right. So what I'm going to do is I'm going to create a node called curNode, and we'll set this guy equal to the current value of head. All right. Now what we're going to do is we're going to set curNode. Well, let's just print out one value. So we're going to say, since curNode currently points to the front, we're going to say system.out.print. I'm going to make this look like a linked list, so we'll do it all on one line. And we'll say curNode dot. Now what I want here is the payload, but we currently don't have a mechanism for getting the payload. So I need to go back over to node here, and we're going to add a get for payload. And then we'll fix the code. All right. So we want to print out curNode.get payload, and that'll print out the current value. All right. Now, we want to do that over and over and over again as long as curNode is not equal to null, right? So while curNode is not equal to null, go ahead and print out the current value of curNode. And then set curNode equal to curNode.getNextNode. So curNode will go from here to go to the same, to point to the same place that his previous next node pointed to. Could be null, right? Next time up, we'll catch that. So it could be null. Now what we're going to do here is after we print out our payload so that it looks like a list, we're going to do a little concatenation thing on here, and we'll put a little arrow on that guy. So it'll be a node with an arrow, and finally that last arrow will point to oblivion. You know, there's nothing off the end of the list at that point. It points to null. So when we finally exit this while loop here, that means that we finally got to our last node. That is, I've printed out the payload of my very last node in the list. Then I printed out an arrow. Then I set curNode equal to his own next node, which finally was null. So at that point, curNode is equal to null. We spin back up. Is it true that curNode is not equal to null? It's not. He is equal to null this time. So we fall past this, and I'll go ahead and do a system.out.println. If you want to actually put in the word null to say that was the end, you can do that. But println will kick it down a line. All right, so that should be our display method. So let's go ahead and let's test this guy. So right now the only way we can add stuff is adding front. So let's go ahead and add some stuff to the front and display it. Well, let's do ll.display first. That should give us just empty list, right? So there's our empty list. Then we'll go ahead and we'll add a couple things here. So we'll do ll.addFront A, ll.add, well, here we'll test on the one list to begin with. So this should just give us A, which points to null. Then we'll do ll.addFront B. Now this should be B, which points to A, which points to null, because we're adding these things to the front of the list, right? So there's our B, points to A, points to null, and you know, you can copy and paste this crap multiple times, and there's a longer list. All right, makes some sense? So that's add front, and that's how display could work. All right, so now we need to go ahead and write add end. Now add end's a little bit trickier, because in order to add end, we need to kind of do something similar to what we did for display. We got to start at the beginning of our list, and we got to run down the line until we get to the end of the list, right? And then we add our new node to that last guy's next node. That puts them on the list. All right, but we can do our shorthand here. So we'll, oh, it's node. I want to be in linked list. So we'll do public void add end, or what, prepend, postpend. What was it? What did the book use? What words did the book use?
Append and prepend.
Append and prepend. Oh, those are stupid names. Add front, add end are better.
The book also had the link list know about tail.
Yeah, we're gonna get there. Because that's kind of our evidence here. Add end is tough if we have to traverse the whole thing, or at least harder to implement,
Right.
or inefficient. If we keep track of the head and the tail of the list, then we can easily get to the very end of the list by just going to what tail points to. Then the implementation of add end is equivalent to add front, just instead of head, it's tail. Okay, we'll write it that way in a minute. But let's write it the cool kid way first, you know, where you feel like you're really working, right? You appreciate that? Not nearly as much as you would if you just use java.util.linklist. Like, yeah, you want to add something to the front, no problem. Up top here, you know, your linked list class just creates an instance of linked list from java.util, and you just pass the buck. Yeah, don't do that. I mean, at the end of the day, I actually don't even care if you do that, but you're only hurting yourself. It will behoove you to practice writing this stuff, because manipulating memory pointers and stuff like that is an important skill. And also with linked lists, and you'll see this in a few minutes, draw lots of pictures. Okay, obviously I have been doing this a few minutes, so I can do a lot of it in my head, but when we do add an index here in a few minutes, we're going to want to draw pictures, because now it's like performing surgery, right? We got this linked list that's, you know, like this, and we want to put something new right here in the middle. So now it's like, okay, I got to hook this guy up to here and this guy up to what this guy used to point to, and you got to make sure you don't lose anybody along the way. All right, so drawing pictures there is going to be helpful, and we'll do that. All right, so add in, the very first thing we need to do is we need to go ahead and traverse to the end of our list. Well, any way you cut it, we're going to be creating our node n is equal to new node, putting our payload in there. Then we'll ask our question if this dot head is equal to null. Then we'll say this dot head is equal to n. Done. Otherwise, we got some traversal to do. All right. So what we're going to do is we're going to create a cur node, because we don't want to change the value of head. And we're going to start at the beginning of our list, and we're going to keep walking until we finally get to the node whose next node is null. That's the last guy, right? So we'll say node cur node is equal to this dot head, this dot hue. I hate this keyword. Then we'll say while cur node is not equal to null, cur node equals cur node dot get next node. Okay, so we're just jogging down the linked list here, okay, till we finally hit a cur node, that's not equal to null. Now we have an issue here though. We're going to run right off the end of the list. So jogging down the list, and all of a sudden I step off the end, and I'm sitting there at null now, and it's like, wait a minute. I need that guy. The guy that I need to add the next node to. The guy I need to add the next node to is the guy just left in the dust. Okay, so I need to keep track of that previous guy. Okay? Or I need to ask a little bit of a different question here. I need to ask, before I just jump ship, I need to say, is the next dude's next node equal to null? Or is myself? Is my next node equal to null? If yes, let's do some connecting of dots before I just go. Right.
Yeah, I was going to ask if you can just say, well, current node dot get.
Yep. So while he wants to do this, while cur dot get next node, or get class, I guess is what we're going with. Get. I don't want to type it all because this keyboard's terrible. All right. Cur dot get next node is not equal to null. Then we'll go ahead and walk the list. We'll set cur node equal to his next node. As soon as cur dot get next node is actually equal to null, then we're sitting right here. And at that point in time, we can say cur dot set next node equal to n. That make sense? All right, so that's an important thing there is we need access to an actual node in order to do something with it. And we need to be careful with linked lists that we don't run off the ends of things or lose track of things. And one of the things that you maybe have read about in the book, have you read about the doubly linked list yet? Okay, so, two-way lists. So in this case, we have a list where you can only go one direction. Okay, and when we start adding in tail over here, now we can start at the end of the list. It might be beneficial for us to be able to walk this way. Okay, which means that now we need to teach nodes not only how to know about their next node, but also how to know about their previous node. Okay, to go back and forth. All right, so let's go ahead and test add end. All right, so this should print out BACD. So there's our BACD. Probably want to make sure you test it on a couple of special cases, like the one list, for example, or the empty list, for example. Well, we already tested the empty list, but or the list where we never add something to the front. Or the list where we add stuff to the front after we've added stuff to the end, blah, 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 all that stuff. All right, so clearly we've exhaustively tested it for all possible bugs. So we're going to say this is good. All right, so that is, and we're going to get rid of this guy because we're not using that anymore. All right, so that's our add front, add end. That was all we were supposed to do for the homework? Okay. So questions about that? Go ahead.
My, the link list LL, like when we do the new link list, it says I have an error.
Says you have an error in this. Did you name your guy link list up here? Can I see it real quick? Oh. It falls into the category. I wrote it exactly like you did almost. Still, all right, let me see. Oh, it's because the name of the file it's in is
Or
I
should I just,
think you can do this. We- Refactor, rename. All right, I'm gonna make this a capital L. And this should be a capital L.
okay.
Yeah, so based on that, now remember that your class name in Java has to match your file name identically, case sensitive and all. All right. So in hers, she had named the .java file linked list with a lowercase l, but her class name here was an uppercase L. But she was trying to create it here with a lowercase l. Yeah, so it's they all need to match up. Okay. So other questions about the solution for the homework assignment? Good with that guy? All right, so now let's look at add at index. Let's get our keynote open here. This is 300. Okay, let's go ahead. Oh, I love drawing. Yeah. Do our linked list here. Oh, something very upsetting happened yesterday, by the way. Let's see if it's still happening. It is. My emojis don't happen anymore. All right, hold on. We got to kill Keynote and relaunch it. No, it's gone. What if it? All right, got it. Nailed it. All right. Can we do like person? Yeah. Love this. All right, so this guy will point to the head of our list. And we'll go ahead and we'll put an A there. Let's give myself a couple more. So that's enough for what we're trying to accomplish right now. Okay, now if we kind of think about this like arrays, or here I'll change my letters too, just so we. This is bucket 0, this is bucket 1, bucket 2, bucket 3, right? All right. So when we say add at index, right now we have add front, add end. So that's effectively saying add at bucket 0, so add at index 0, and it's saying add at index, I guess depending on how you want to write this, if this is 0, 1, 2, 3, add at index 4, the place you ultimately want it to end up, okay, is typically how we think about it. Otherwise, in order to get, if you said add at 0, you actually mean add it after the guy at 0. That might be another way of thinking about it. But usually you say add at index, you want the node you're adding to become the new that index. Okay? Well, so if we say add at bucket 0, we can just call add front. So add an index for 0 is always add front. That's an easy one. Now, add at index, in this case 4, means add end. But we don't necessarily know that because getting our count is more difficult right now, correct? So for right now, if I want to figure out how many elements are in my list, I come into linked list, and we're going to say public int get count. Okay, and this guy's going to have to walk my list from beginning to end, counting the number of nodes he came upon. All right, so we'll have an int count is equal to 0. We'll say node, cur node is equal to this dot head, while cur node is not equal to null, count plus plus, cur node equals cur node dot get next node. Then ultimately return the count. All right, so every single time we want to know the count of our lists, we have to go through and traverse the entire list, counting every node we bump into. So if we go back here to driver and we test this, so I should have, what, 4 guys in here? We'll do system.out.println ll.getCount. So there's my 4. All right. Now we can look at that and say, okay, well, this wasn't all that hard to write, and there's benefit to writing this because we've already seen in the last 15 minutes or so, we've pretty much written this same pattern 3 times, right? That kind of go-to move for traversing a linked list must be something that is somewhat important to linked lists, right? All right, so we've been practicing this pattern. Now, at the same time, though, we can say, you know what? There isn't a great reason why we can't just keep track of count as we go. We know that whenever we add something, count goes up. Whenever we remove something, we don't have that implemented yet, but when we do, count's gonna go down. So can't we just do it while we're adding and removing things and save myself from doing calculations every single time I call get count? So we might want to have a private variable up here. And when a linked list is first created, we'll set this dot count as equal to 0. Whenever we add front, regardless of whether we're doing it in the if statement there or whether we're doing it inside the else, this dot count becomes 1 larger than it used to be. Whenever we add end, regardless of whether we're doing it based on the empty list or we're doing it that way, this dot count plus plus. So then for get count, we just have to return this dot count. And we get the same answer. Okay, but this time we can call get count hundreds of times and we're not doing any extra calculations. It's just resolving a variable. That make sense? We're just keeping track as we go. That makes life a little bit easier there, but then also gives us for adding an index, since every single time added index gets called, we're going to determine whether or not we have one of the easy solutions, right? Okay, am I actually adding to the front? Why don't I just call that guy? Am I actually adding to the end? Why don't I just call that guy? Well, to ask the question, am I adding at the end, I need to look at my length, correct? The number of elements that are in there. And if what I'm adding to is equal to that, to my count, then I'm adding to the end. If it's greater than that, or it's less than 0, then we do our little runtime dealy, like just say, hey, you, that's not a legal index or something like that. All right, so let's write add an index. Okay. Whoop. Now, before, and we'll write our algorithm for the else here, using pictures here in a second, but before we actually create our node n, we want to go ahead and find out if we're actually going to leverage our add front or add end. Okay? So we'll ask the question if, oh, sorry, I need an index here, right? So if index is equal to 0, then let's just go ahead and call this dot add front, passing it s. Else if index is equal to this dot count, we'll call add end, passing it s. Else if index is less than 0 or index is greater than this dot count, we will throw new runtime exception there. Sometimes we'll go ahead and give it the index. Nice pretty error message. So we'll create a new runtime exception. Hey, that isn't a legal index, showing them the number that they passed it, which will be something that's either less than 0, so some negative number, or something that's greater than count. So we'll scream at them. Else, do the hard part. Okay, that's where we actually have to do the, let's find the place we're going to add this and add it. All right, so let's test those first three real quick. Just make sure that they're doing what we think they're doing. So rather than add end and add front, we're going to go ahead and we're going to say ll.add index. We'll add an A at index 0. We'll add a B at index 1. So that should give me the list AB. And then let's do a C at index 2, which will be the new end, right? So this should give me the list ABC when all is said and done. There's ABC, count was 3, seems to be okay. Let's go ahead and do our add at index -4, should scream at us. Yeah, see, I ran into this yesterday. Is it one of these guys? No, that's not the guy. Hey, that isn't a legal index, -4. I give it 10, same thing. Nope. Nailed it. All right, so that's not a legal index. So it seems to be screaming at us in all the right places, right? All right, so now we got to write the difficult piece here. Let's go back to our picture. So we know that the index was passed in. A is a legal index. B is not the front. And C is not the end. So it's somewhere in the middle. Love that guy. It's one of the Bethesda students. It would be even better if he had a real trumpet. Just like marched around campus. By the way, you should ask Dr. Wall about his banjo. He has it with him in the office. Maybe he'll. Yeah, I was sitting in my office before class today, playing this. Hopefully. After I saw him walk in with it. All right. So we know we're dealing with something in the middle here. So let's assume we're adding it at bucket 1. So we want our node to be the new bucket 1. So let's steal one of these guys. So we're going to add E at index 1. So ultimately, I want the E to be the new B and B to get shifted over some. All right. So how does that have to happen? How do we make that work? Well, if we just look at the picture here and we're thinking about how we're ultimately going to connect this up, we need E to point to the same place as A points to. So we want E to currently point to bucket 1. Okay, our brand new node is going to point to the same place as the place it's going to overrun, right? So in order to do that, in order to get bucket 1 here and get that place that we're pointing to, we need to ultimately traverse to A. So we need to traverse to the guy right before bucket 1. All right, so we need to do this 0 times. So what we're going to do is we'll go ahead and we'll create our node since we're in charge of actually adding it. The other ones we used add front and add end to add the node, which that guy already creates a node for us. So we'll create our node end, which is a new node, passing it S. All right, well now we need to go ahead and move kernode to be the place that is right before the place we're adding it. So we'll say node kernode is equal to this dot head. So we'll start at the beginning, and then we need to move not to index I, or index, but 1 before that. Okay, so we want a for loop that's going to go through a certain number of times. So if index was 1, the for loop starts off at head and goes through 0 times. We're already where we want it to be. If index was 2, we're going to start at the head and go through 1 time. So index minus 1 number of times. Okay, so for loops lend themselves to counting problems where we know how many times we want to loop through. The number of times we want to loop through here is index minus 1 number of times. And each time through, set kernode to his next node. Make sense? So let's draw our kernode down here. Okay, so right now, we start kernode pointing to the same place as head points to. Then we're going to loop through setting kernode to his own next node, index minus 1 times. Current I is equal to 0. I is less than index minus 1. I plus plus. Kernode is equal to kernode dot get next node. Okay, so this will take kernode on a voyage. Remember, for loops are pre-check loops, which means we check this Boolean expression before we execute the body of the loop even once. So if index in this case is 1, we're saying I starts off at 0. Is 0 less than 1 minus 1? Is 0 less than 0? It's not. We don't do this even 1 time. So kernode is still pointing to this dot head, which in this case happens to be the guy we want him to point to. If we had passed in index 2 instead, so we actually wanted to have it replace here, I starts off at 0. Is I less than 2 minus 1? Is I less than 1? It is. So we'll go ahead and set kernode equal to his own next node. So kernode will move from here to here. Then I becomes 1. Is 1 less than 1? It's not. So we're done. We've moved him into position. All right. So what we know after this for loop is done is we have moved kernode into, let's see, into the position immediately before index. Okay, that's what we've accomplished up to this point. We've built the new node we ultimately want to add, and we've moved cur node to be at the position right before it. That make sense? See how these pictures kind of help? All right, so things look like this right now, and this is node n down here, and this guy's next node by default just points to null. Okay, so what I want to have happen next, I can't disconnect anything, because understand that if I do this, if I say, oh, okay, we'll just set cur node's next node equals this dude, I just abandoned half my list. This guy's node pointer goes down to 0, garbage collection comes and cleans him up, and all is lost. And once he gets cleaned up, this guy's node pointer goes down to 0, and then he gets cleaned up. Okay, I mean, we just set things up for a massacre is what happened. All right, a Java garbage collection related massacre. So we can't just haphazardly move pointers. We have to do them in a very specific orders to maintain everything. Okay, so the next thing we want to do is we want to set n's next node equal to cur node's next node. Have those guys point to the same place. Make sense? So we'll set say n dot set next node to cur node dot get next node. So what that does is this right here. N's next node points to the same place as cur node's get next node. Okay, so both of those guys are pointing to the same place, which then frees us up to make cur node point to n without losing anybody. Okay? So now we'll say cur node dot set next node to n. And now things look like that. And have we inserted E at, I guess in this case, bucket 2. That was the example I ended up following through with. So this is bucket 0, bucket 1, bucket 2, and the guy that used to be at 2 is now at bucket 3. Shifted everything down. Make sense? Okay, so let's go test this. So we got 4 things there. Now let's do, actually this one's going to be an error, right? Here, we'll just do add end on that guy. All right, and then we're going to go ahead and, so this will be 0, 1, 2, 3. So if you want to add it 2, just do our test. So we'll add an E, we'll literally match what we did. So we'll do add at index and E at position 2. Then we'll display. So when this is done, we should have at bucket 0 as an A, at bucket 1 as a B, at bucket 2 as an E, at bucket 3 as a C, and at bucket 4 as a D. A, B, E, C, D. Okay. Let's make sure this also works if we pass in a 1, which means our for loop actually doesn't execute, right? We still write the for loop because we say, look, this is how many times I want you to traverse. But it actually, because it's a pre-check loop, won't traverse at all. We just, cur node starts at head, and that's where it stays. So this is going to put E at bucket 1, so we should have A, E, B, C, D. Make sense? Okay. And we can keep going. I think 3 ends up working, right? So there's our E at bucket 3. 0, 1, 2, 3. All right, so that's added index. Not horrible, but a little bit complicated. So what else might we want to do? maybe, oh, go ahead. Remove an index. Yes, that's a very good prediction for what your homework's going to be. Maybe I'll help you write remove front and remove end first. You know, the easy ones. Because I struggle with hard problems usually. It's like, I'd rather you guys do it, and then you can give me the pointers when we're... Actually, what I really struggle with is getting tennis ball emojis. The things I'm enamored by. See, oh, he's got a little, look, he has a little Apple laptop. That's so cute. Oh, you want to see something funny real quick? Mr. Gonzalez has a Superman cape.
He has a pretty big wardrobe these days.
He does have a big wardrobe. I also have a Superman cape, by the way.
Yeah.
There's mine.
Nice.
So Mr. Gonzalez saw mine, and he decided he needed one. And there's your example of where Superman hangs his cape. Hang it next to the big screen. I have actually found that cape does not provide the lift required to... I've actually decided that Superman's cape has very little to do with his ability to fly. But little kids don't get that, right? How many of you put a cape on and tried to like jump off something too high? You can admit it.
It's like in the
How high?
Not
Oh,
very.
oh, well, we were. I jumped off our roof. I tell you what, I wasn't right for a while. because I landed, and you landed and you try to absorb the shock into your knees, so you like squat down. But like, I squatted down really hard. And like my neck wasn't right, my tailbone fell off, And I was old enough to know better. I mean, I was like 10 or something. I mean, I was already writing software when I jumped off the roof with a cape. I mean, that's the kind of mentality you're dealing with here. That also reminds me. Do they still play? Do they still have laser tag?
Yeah.
Like you can get the home laser tag kits. Because we had laser tag kind of I think when it first came out, and we had this giant. Pine trees, the Christmas trees, right? But like a really tall one, must have been there for 100 years or something. So this thing was probably 60 feet tall. And we used to climb up the middle of this thing. So my brother's up on top of this thing, and we're firing at him. And I mean, this kid goes into a free fall coming down this tree, hitting every branch on the way down. Okay, it slowed him down enough that he just hit the ground, but he was fine. And he must have got shot 6-7 times on the way down. Hit the ground, turned it off, back on, said, "You missed me," and ran off.
Oh.
My brother's like the biggest cheater. It's so bad. He totally did that. That kid.
Does he admit it now when he tells the story?
Oh, yeah. Because him and I talk all the time, because now he's a dad. And so he's got see, Asher is 10, maybe 9 or 10, 11, his oldest, and then the youngest is 4. And so it's like when kids do funny things, right? And so like as a parent, you got to like really try sometimes not to laugh, because you're supposed to. No, that's bad. That's very bad. Like I think one time, actually, it might have been the older one. I think he went to the bathroom and decided that would be a good thing to throw at his brother. And that's hilarious, right? But I mean, you can't pretend like that's hilarious. That's bad. If you're going to do that, you do that at public school. Yeah. Oh, what are we at? Remove? Remove it. All right, so we'll write remove front, public void, remove front. And we can actually have this guy, why don't we have it return the payload that we're removing? So rather than the node itself, because when you think about the people that are going to be using our linked list, a node object isn't all that useful to them, right? So when you say I'm removing something, you really kind of want the value. Like, give me the value at bucket 4. Okay? And actually, we might want to write that real quick too. Just get at index. So let's actually write that real quick. All right, so public int get at index. So this guy's gonna.
That should be a string if you want to return payload.
Yeah, it is. Thank you. Yeah, I'm stuck on your quicksort. Yeah. I mean, why was it okay for you to sort ints and it's not okay for me to return an int? Yeah, I get it. Double standard, right?
You've been doing this for a few years.
This is garbage. Well, yeah, but I mean, so I'm old and senile. I mean, I don't know any better. You're young and your memory's still intact. I have no idea what I had for breakfast. I just don't know. All right. So get at index, we'll do the whole, if it's less than -1, you go runtime, blah, blah, blah. So here, if index is less than 0 or index is greater than, actually we want to have greater than or equal to count, because if we're treating this guy as like an array in terms of buckets, count is actually the one off the last legal bucket. So the last legal bucket is count -1. If we're keeping it consistent with, it's our linked list, so we can choose, but that seems to be what we're doing here. I'll go ahead and steal my runtime error from down here. Nailed it. All right, else. They must have given me a legit thing, so I need to move to that index. So we'll say node, cur node is equal to this dot head. Then we'll do our pre-check for loop again to zip that many times to get me to that place. So for int I is equal to 0, I is less than index, I plus plus, cur node is equal to cur node dot get next node. Ultimately, we will return cur node dot get payload. All right, so there's our get at index. Test that real quick. All right, so let's see. This guy currently looks like A, B, C, D, E. So this is 0, 1. Let's do a 1 and a 3. So we should get a B and an E. So there's our B and our E, and we continue to remind everybody what our count is. All right, so that's get at index, but so understand that, I'm going to eventually get back to the code. There we go. Understand that get at index does not remove something. So your code for your homework, which is going to be remove at index, that guy is going to do some similar-ish stuff to this, except before he returns the payload, he actually has to, surgically remove him from the linked list. All right, so let's go ahead and let's quickly write remove front. All right, so we'll do our similar thing here. So if this dot count is equal to 0, let's throw an exception. Maybe something like can't remove from the empty list, something like that. Okay, else, if we're removing from front, then what we need to do is we need to hold on to the guy we're about to remove. So we need to preserve the current value of head, then make head point to his own next node, right? Then make the current guy unset his next node so that he's free. Okay, so if I'm removing this guy right here, I'm gonna take cur node and we'll have two different guys pointing to the same place here. All right. So now what I'm gonna do is I'm gonna have head traverse to here. That's the new front of the list. But then I'm gonna go ahead and set cur node's next node to null. That way the pointer count is correct. Realistically, this guy will fall out of scope, so actually it will get garbage collected anyways, but I think this is more thorough. Then I'll go ahead and return the payload of that guy. So this is going to be node cur node, well, let's call it node cur front is equal to this dot head. This dot head is equal to this dot head dot get next node. Cur front dot set next node equal to null. Then return cur front dot get payload. All right, so that'll remove front. Let's test that, make sure that's the case. So front here is going to be our A. Or whatever. So there's our A, the guy that we removed from front. But let's make sure we left the rest of the list intact afterwards. So we'll print it afterwards. So before we remove A, it looked like that. Then we removed A, and this is what it looks like afterwards. Make sense? All right, so for your homework, you actually have two things. You got to do remove end. So public string remove end. And then public string remove add index. Those two dudes. Make sense? All right, I'll go ahead and paste this current code up on Slack. I probably don't need to paste node, do I? I think node's pretty self-explanatory. Okay. Code snippet. Paste. Code was it 16 to 16, 17? Nailed it. Okay, we're out at 11:20, right? Is that the right time? Okay. I will see everybody on, what day of the week is it? Thursday? I'll see you Tuesday. All right.